So we are in the middle of worksheet 6 and then eventually 7 today. We're going to finish up our lesson on transformations, but first we're going to warm up with what you guys know from Algebra 2 already, I hope. This is not on your worksheet anywhere, but you are just going to look up at the board and tell me the transformations that you see. So the parent function is just your normal f of x equals x to the third power, the cubic function. Can you tell me the transformations that were applied to each of these examples? Adam, start with you. What is this transformation? Down 5. Very nice. Kira, what transformation is that? Very good. Nice use of the opposites with the built-in negative. And then over here, let's go Riley. I got 2. Yes? Very good. So that last function had 2 transformations. If I move left 2, does that change your x value or your y value of an ordered pair? It's just an x change, yeah. And if I move up 4, does that change your x value or a y value? A y. So then you're probably wondering why I'm asking you this, and that's because in Algebra 2, once in a while, you guys would get something like this. And your teacher would ask you to identify the 3 transformations that occurred. And there are 3 transformations there, right? And an Algebra 2 student would say what? Oh, only if you're very advanced, Taylor. First, usually, and I'm just saying from my experience, usually kids go right 3, then they go up 4, and then they tell me vertical stretch of 2. And that was fine for Algebra 2, because we were just having you identify them in particular. That's not going to be good enough for PreCalc, though, because I'm going to ask you in which order were they applied. So the right 3 is an x movement, up 4 is a y movement, and a vertical stretch, what does that change, x or y? If you stretch things vertically, you're stretching their y values. So the problem is these 2 shifts affect the same variable, which means the order in which they're applied is going to make a big difference. And we didn't make a big deal about this in Algebra 2 because we didn't really care yet, but we care now in PreCalc. So if a PreCalc student told me that this occurred first, then second, then third, they're actually very, very wrong. Let me show you why. If you take the parent function of x to the third power and you start shifting it right 3, that's fine. It's minus 3 squared. And then if you shift everything up 4, they would put a plus 4 here. I got nothing wrong with that so far. And then if you apply the vertical stretch here at the end of your problem, it looks like this. Uh-oh. What changes? I mean, that vertical stretch factor, yeah, that's definitely a 2 there, but what else is going to get hit by this 2? And then this becomes a plus 8 at the end, which is not at all what we wanted originally. So the order in which you apply 2 transformations that change the same variable makes a big old difference now. So if this was a PreCalc question, what I'd be looking for is that you applied the vertical stretch before you applied the down 4 shift. It doesn't really matter what order it shows up in the list, but the vertical stretch would have to show up first. Because if it shows up after the vertical shift, then everything got multiplied by that 2, and that's the problem. All right, we're going to see a lot of that today, and that's probably the toughest part of the lesson. So we've talked about reflections already. That was yesterday. This is the order of operations, order matters thing. So look here, guys. This is from your textbook. It's not in your notes anywhere, I don't think. This function, g of x, compared to this other function, g of x. Now, first of all, since you in the back can't see it, here's the origin, and here's the origin. And I'm thinking y'all can see, no matter where you're sitting, that this guy, this green guy, isn't looking a thing like this blue one. And that has to do with the order in which they applied the transformations. So this one right here, the big difference is this one has the reflection applied first, before the plus 2 shift, and this one has the reflection applied at the end of the problem. Because what's going to happen to that plus 2? It's going to end up being a down 2, which is why you see it located down here in quadrant 4. Okay. I see your confused looks. That's the right look to have right now. Let's see some examples of this, okay? But first, we got to revisit your chart. We have a couple more transformations to talk about. This first one should feel very, very familiar to you. This is from your textbook, though. You're not on your chart quite yet in your notes, guys. A vertical dilation, which you guys called a vertical stretch a few minutes ago, okay? In Algebra 2, you guys referred to these as vertical stretches when you threw an a value out in front of your function. And your book gets fancy, and it calls it a vertical expansion if your a is greater than 1. And then it calls it a vertical compression if your a is between 0 and 1. So I want you to kind of recognize what your book did, because they're going to draw a lot better than I will. This blue one is the original parent function. And then when they vertically stretched it, that's when you little kids back in the day used to say it got skinnier. Yeah, it's called a vertical expansion, or I'll accept vertical stretch in PreCalc still. So a vertical stretch of whatever factor it is. So that last example that Taylor was talking about had a vertical stretch of 2. But look what a vertical compression does. The little kids told me it got wider, but what's happening is your vertical components, your y values, are going up slower. So instead of like reaching up to a 4, they're only going to reach up half as much. It's only to a 2. So that's why you get this vertical compression factor. It makes it look wider than it is. This is a new one for you guys. You can have horizontal stretches and dilations too. So horizontal meaning the x's are being changed. And the way it looks is the a value is going to be inside of your function, inside of the parentheses. So inside of your function notation, remember guys, anything in math that's in parentheses, usually we have opposites going on. And that happens here as well. So you're going to have a compression if your a is greater than 1. So if you're inside of your function with a number bigger than 1, that's actually going to compress it horizontally. That's weird. And then it's going to expand it if you have an a value bigger than 1. So like this example right here, the blue one is the parent function. And then this green one, I know that looks a lot like a vertical stretch, doesn't it? You're looking at that going, how is that different? It's going to be different. I'll show you why it's different on some upcoming functions. The reason this one that looks like a vertical stretch is because there's only a singular x-intercept, and we'll see some weird ones coming up. But you guys are okay with me calling this a horizontal compression? It takes your horizontal pieces, your x pieces, and pulls them in, compresses them. This one's called a horizontal expansion. All right. Let's take it. Hold on a minute. To your chart. All right. So let's talk about the old stuff first. If you have an a value out in front of your function, that's going to be a dilation in the vertical direction. This is the one you guys are used to. And if your a is greater than 1, you're going to have an expansion, or you can call it a stretch, a vertical stretch. So some examples of that would be like 2 times f of x, 4 times f of x. Those would all be vertical stretches. But a vertical compression, and that's the word I'd like you to use, compression, is if your a value in front is something between 0 and 1. So something like half of f of x, or 2/3 of f of x. What variable is it going to change if you're multiplying your function by half or by 2? Is it changing the x or the y if it's a vertical dilation? Vertical meaning y's, very good. So both of these are going to affect the y values. All right, but let's talk about the new one. This is a weird one, guys. Make a couple notes to yourself. This is going to be extra weird. The a value is inside of your function notation. It's going to be opposite of what logic tells you because it's in the parentheses. Think of it that way. It's going to be opposite of what you're thinking originally. And then another note that I want you to make, it's going to change the x-intercepts. I think that's probably the easiest way for a pre-calcer to recognize that you have a horizontal contraction or compression is if your x-intercepts are changing. These are hard to tell. These are really hard to tell. All right, so what would that look like in function notation? So if you have a horizontal compression, that means inside of your function, you're going to have a number bigger than 1. So like this, f of 2x. That's going to be a horizontal compression, and it's going to take your x-intercepts, all your x values, and it's going to shrink them in by a factor of 2. So then some kids are like, well, should I call it a horizontal compression of half then? I'll accept that. And then someone else says, well, can I call it a horizontal compression of 2? And frankly, I'll accept that too. The fact is you use the word compression. So you're telling me it's being pulled in from the center. Okay. So horizontal expansion, because we're weird and opposite, that would look like this. So there's a number inside of your function that is between 0 and 1, and that's a horizontal stretch or a horizontal expansion. It's going to expand them out by a factor of 2. How confusing. Thank you, math, for being extra weird. Now, we talked about this briefly yesterday, guys. Remember, the reason the parentheses are always working in opposites of your logic is because you're always trying to figure out how do I get back to the original. So if you're moving horizontally out by a factor of 2 to get back to the original, you'd have to multiply it by 1/2. So that's why they're opposites. That's a little like a lot of thinking for a Tuesday morning. So if all you think about today is that they're affecting... oh, by the way, what are they affecting? Your x's or your y's? Yeah, these are going to change your x's. Okay, now for the weirdest ones. The absolute values. Okay, so I'm going to steal these drawings because they're drawn for me and I don't have to draw anything, so I love it. If I take absolute value bars and place them about your function like this, what it does is it takes any negative output piece of your function, so anything that dangles below the x-axis, and it reflects it up. So you guys, little kid definition of absolute value is to, quote, make it positive. So it takes all of your negative y values and it makes them positive. And the way you look at that graph is it reflects them up to the positive land. So this is what it ends up looking like. Isn't that beautiful? And then now for the weirdest one ever. Ready? If you throw your absolute value bars inside the function itself, around the variable x, or whatever x is doing, what it does is it takes the negative side of your graph, so this part right here, and it's going to erase it. That's what I want you to think of it. It's erase it, totally gone. And then it's going to take the right side of your graph, and it's going to copy it and reflect it. So it makes another copy of this little blue piece, but it reflects it over yonder. So like, yes, I'm supposed to be able to draw that. Hey, that was almost good. Okay, this is what it looks like. Interesting. Isn't that very interesting? Why would I ever want to know that? Because you took PreCalc. So by default, you want to know this, right? Okay, so now we all get to have fun watching Mrs. Abruzzo try to draw something. Well, I am going to draw a very boring parabola to start us off here. It's going to hang below the x-axis. Sure, like this. So if I put absolute value bars about the function, this is just like it shows here. It says it makes all the y values positive. So I'm going to take all of the y value pieces that hang below the x-axis, and I'm going to reflect them up here. So these aren't here anymore. Gone, 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 gone. And you end up with... And you're all in for a treat because there's a whole bunch of this stuff on your homework tonight, which means when I made my key, I had to draw all of these. So my key is really hard to read in the PDF format of how I post it on Google Classroom. If you'd rather take like a photo, a color photo on your phone of the key, because I did do it in color, it's a little easier to see. So there's a lot going on that key, man. You're going to want graph paper for your homework tonight as well. I do have some in the other room I can grab. All right, now for the super fun one. Can you guys graph me a function? But I need you to make it kind of weird. So, like, I don't know. How about... I don't want like a traditional parabola, you know? All right, so here's what we're going to do. We're going to take this part. Do you remember what we do with the left side? We remove it. We erase it. Cool, cool. Do you remember what we do with this part? Copy it. Oh boy. And then once we copy it, we have to reflect it. Now I think, if I did it right, probably not. I think I can copy, but I don't know how to reflect. That's my problem. Ah, forget it. You know what? It does say flip? Yeah. Oh, blessed. All right. Let's paste it real quick. Oh, And then flip it. Yeah, look at that. Left, right. Oh, I did the wrong one. Up, down. Did I just pull the... Oh. There we go. Oh, it took my text too. Oh, you know, whatever. Boom! See? Isn't that pretty? That was nice. All right, so, yeah, that's totally what it looks like. Wow. Guys, that's weird. That's a really weird transformation. The good news is on a test, I'm not going to make you do any like hand renditions like I just had to do, but I will have you recognize that that transformation occurred. It's actually a pretty easy one to notice when you have a graph and a parent function. It's just really hard to draw because it involves erasing things and copying things. Unless you have a smart board. You don't have a smart board. All right. You do? Oh, that's cool. What? The last one? So this green piece gets reflected over the y-axis. So this other green piece shows up. So I should come through and I should erase this, huh? Because this isn't here anymore. So just this green piece is the new function. Over here? Over here. This piece. Yes. Oh, who's changing? Well, this is confusing because a lot of things change. So don't worry about this. I mean, this one, like, clearly it changes the y values and the x values stay. But this one's like a big question mark to me because, like, so many things change. I don't even know how to answer that. I guess don't worry about it. I'm not going to make you answer that question in the future. Could you find worksheet 7? We're moving on. All right, so this example's already done for you, thank goodness, because if I had to draw this again, we'd all be in trouble. But let's talk about what they concluded. So the parent function, if I took away all the transformations from this function, they would be left with the parent function of this. So just the square root of x, which they graphed for you here. This is out of your textbook. This is the parent. And then it asks them to identify the two transformations and then graph the new one. This is what we're about to do together in a moment. So, are you okay with agreeing that they reflected across the y-axis? Oh, did we do reflections yesterday? Yes, we did. Okay. So, are you okay with that being the negative inside of the function itself? Remember, that's the new reflection. You guys are used to reflecting over the x-axis. Well, if they put a negative inside the parent function, that's going to be a reflection over the y-axis. Okay, the other transformation that they identified is this right here, is a down 1 shift. So question for you. If I reflect across the y-axis, are you changing your x values or your y values? You're changing the x values. And if I shift everything down 1 unit, are you changing your x values or your y values? Why? Since these are two different variable changes, that means you can apply this change in any order you want. So order wouldn't matter. So if we were doing this one by hand, here's what I'd make you do. You'd start with your ordered pair at 0, 0. Right, that's 0, 0. And then I would apply those two transformations. So the first one being reflecting across the y-axis. Well, that's boring. You're on the y-axis. So when you reflect over it, you just stay there. So you don't move from 0, 0. But if I shift that point down 1, are you guys okay with me landing right here for the new point? That's where they have it, so I hope it's right. Another ordered pair that I see on this parent function, I'm going to use 4, 2. This is the ordered pair 4, 2. Guys, if we were going to reflect this across the y-axis, where would you land? At negative 4, 2, which is up here. But then I'd have to take that point and also shift it down 1. So that's why they plotted this one. And once you get a couple of points plotted, then you connect and make your new function. That's what we're about to do here on these next few examples. Like this one. All right, teamwork makes the dream work, y'all. Who is the parent to this function? Take off all the transformations and just give me the boring parent function. I don't like how we call the boring function the parent function, by the way. I feel like there's something implied there. Sorry, parents. All right, so the boring function is just plain old absolute value of x. So on your graph, I'd like you to plot sketch out absolute value of x, which you could use your graphing calculator for, guys, but this is a pretty easy one to plot by yourself. The vertex starts at 0, 0, and then it's a case of like up 1 over 1 everywhere. Now, these are counting by 2s, but that doesn't change the fact that your branch has a slope of 1. So I'm going to just plot a few points here. Good enough. All right. There's the parent. Oh, for Pete's sake. All right. So this is the ordered pair 0, 0. I'm going to talk about this ordered pair 4, 4. And then over here, how about we talk about this ordered pair negative 4, 4 in a minute. Okay, 2 transformations that occurred. Can you identify them for me? Starting with, oh boy, who knows what to call that? Okay, so let's call it a vertical compression, because the 0.5 means it's going to get squat, right? Vertical compression of half, or 0.5. I like it. And then what variable does that affect if you vertically compress something? Does it change your x values or your y values of your ordered pairs? Vertical meaning y. All right, how about this x plus 4 factor? What does that do? Left 4. Does that change x's or y's? Left moves x's. All right, good news. They don't affect each other, so you can do any order you want. All right, Daniel, help me move 0, 0. All right, this is a weird question. I want you to vertically compress 0, 0. So you take your y value and you multiply it by half. It stays at 0, 0. Yeah, I like 0, 0. But now I need you to shift it to the left 4. So over here at negative 4, 0. Cool. All right. Miss Riley, this is the ordered pair 4, 4. Okay. I want you to do those 2 transformations. We'll stick with the same order. So what would it look like if you vertically compressed it by half? So that means you take your y value and you shrink it by half. Where are you at now? You're still at over 4. That didn't change, but now you're only up 2. So 4, 2. So now take that point at 4, 2. Don't mark it down yet, because you still have to shift left 4. Where are we going to be? At 0, 2, right here. That is not a point. I just keep making it worse. Okay, I just keep making it larger. Okay, so, and what I don't like, and your book does this all the time, they count by 2s, which I forget like halfway through the problem, that they're counting by 2s, and then I move the wrong. So just, when you are doing your homework, don't count by 2s, and you'll be fine. Okay? Ms. Taylor, can you help me move this ordered pair, which is at negative 4, 4? So the first thing we're going to do is we're going to vertically compress it by half. Still over negative 4, but now it's only up 2. So negative 4, 2, cool. And now I want you to move it left 4. Over here, yeah. Yeah. Cool. I have a lot of points, and I don't even know what my points are anymore. This ugly thing is a point, right? And this is a point. There we go. That was the vertex that Daniel moved. Ooh, yuck. Okay. Lovely. Okay, so you have an absolute value graph. That was definitely vertically compressed by a factor of half, and then it was shifted left 4. That wasn't too bad. And this is the kind of thing you're going to have to do on your homework. You're going to graph the parent function, and then you're going to strategically move them. Sometimes order matters, sometimes order doesn't. Let's talk about these 2 transformations. First, let's talk about our boring parent function. The boring parent function would be taking off all the transformations. So Jasmine, who's the parent function here? If you took off the 2 and you took off the down 4, you're just left with x squared. So let's graph a nice parabola. And you can graph any points you want, guys. So I'm going to pick things that like I can graph easily. Like I'm thinking 2, 4 is a nice point. So negative 2, 4 would be a nice point. And I'm probably going to label them also because look at that. They're graphing by 2s again. Why? All right. Oh, geez. Okay. Helps if you actually hit the point, but whatever. Okay, so we have 2 transformations. I'll talk to poor Jemiah. She doesn't have a voice today. Enrique, tell me a transformation you see. Well, I'll tell you one I see. You tell me what it is. What does this do? So it's a dilation in front of the function. So is it a vertical stretch or a horizontal stretch? If it's in front of the function like this. It's a vertical stretch of 2. Oops, that's an E. What about this transformation, Enrique? What's this one? Take a guess, and we'll talk about it, whether it's right or wrong. It is down 4. Okay. So, stretching vertically, Brandon, does that change your X's or your Y's? Okay. And then moving down 4, does that change your X's or your Y's? Uh-oh. Both of these transformations from Enrique affect the Y's. So now we do have to watch which one happens first versus second. Huh. Anyone have any thoughts? Yes, you can follow order of operations. But then you're like, wait, is this one of those times where it doesn't mean that? Because remember, there's times in math where you do opposite of PEMDAS? So what do you think, Daniel? Does the vertical stretch come first or second? Okay, you're right. Can we talk about why it can't come second? So if you do the downshift first, and then afterwards I come back through and I apply a vertical stretch, you would have to apply the vertical stretch to everybody. And what happens to that last term over here? It becomes a -8, which is not at all what they wanted me to graph. So you are 100% right. This is the first shift we have to apply, and this is the second shift we have to apply. If you went against me and did it opposite, you're going to get a very different graph. You're going to get a parabola that has a vertex down at -8, 0, -8, which is not what we have. All right, here goes the fun times. Let's talk to Aiden. Take your point 0, 0, and in this exact order, Aiden, I want you to vertically stretch it by 2. Well, how do you stretch a 0 by 2? You don't. Don't overthink it. But you can shift it down 4. So 0, 0 stretch doesn't go anywhere, but when I shift it down 4, where are we at now? Yes. All right, Aiden, keep going. This is the ordered pair 2, 4. I want you to vertically stretch it by 2. So that means you take your Y value and you multiply it by 2. So where does that end? 2, 8. And now I want you to shift it down 4 units again. Yeah, you end up back here. That's weird. All right, so the same thing happens here, right, Aiden? You stretch it and then you shift it back down 4. So we end up with a really ugly parabola, apparently. Daniel.
Would there be an instance in which we'll do the translation?
Yes, but it would have to look like this. So if...
Oh, that's how it's different.
The distribution, yeah. So sometimes kids get crafty because what's going to happen in PreCalc is you're often going to have to give me the function. Like I give you the graph and you got to come back with the function. So there's more than one right answer. Like for instance, this thing I just wrote down in blue is this exact one. It's the same function. So if you knew to factor out the 2 and apply the vertical stretch afterwards, that is amazing. I love that. Most kids don't see that. Because imagine this, guys. I'm going to give you a graph that has a parent function and then a transformed function next to it. And you have to come up with the function itself. So some kids look at this and go, oh, well, it was shifted, it was vertically stretched by 2 and then shifted down 4. And some kids look at it as it was shifted, they might think it's shifted down 4 and vertically stretched, but we'd find out that that's not actually what happened. So as your teacher, I'm going to tell you that this leaving it undistributed is not usually in anyone's benefit. Okay? Kids kind of stumble upon that version of it, but very few kids can see that in a graph. Okay? So you talked about order of operations earlier. This is a good case of you would do inside the parentheses first, right? And then you distribute the 2 after it, so the vertical stretch would be secondary. Yep. These can get real weird, man. All right, good news. The next one should kind of alleviate your pain. It's not too bad. Sorry, I spoiled it. Girls, ready to talk to me about transformations and parent functions? Sure. Fight over it. Who's going to tell me what the parent function looks like? How do I graph this? I want numbers that are really nice to take square roots of. Like 0's good, right? What happens when you take the square root of 0? 0. 1's nice. 1 square rooted is 1. The next number that I like to take the square root of would be a 4. And that output would give you a dose. And then I'm going to fall off the graph after this. So here's your boring parent function. All right, girls. Teamwork now. What are your two transformations? This is up 1, yep. And left 3. See, teamwork was fun. Now, left affects which variable? X. Up affects the Y. They do not compete against each other, so you can apply this in any order you want. All right. Class, all together now. Take your point 0, 0. Shift it left 3 and up 1. Boom. Take your point 1, 1. Shift it left 3 and up 1. Boom. Take your ordered pair 4, 2. Shift it left 3 and up 1. Boom. And then try not to ruin it by graphing an ugly graph. Fail. Actually, that was pretty good. I'll take that. Well, it wasn't a competition, Daniel. Thank you. Thank you for the backhanded compliment. All right, so there's your graph. So that's like a Algebra 2 question. We didn't usually make you guys graph them on the same coordinate plane, but that is something in PreCalc we'll definitely be having you do. Notice what we haven't touched at all today, guys. I haven't touched our graphing calculator at a single moment because A, we don't need to, and B, the questions that we're going to be asking you are not doable on the graphing calculator. It's going to be a lot of graph interpretation. Ooh. It'll be functions you won't know how to graph. They'll be weird and funky. You're not going to like them. All right. Oh, boy. I hate to loop around and get more kids involved in this one, but class, can we talk? Parent function, absolute value. You don't have to plot every single point. I'm just going to like strategically plot a couple of them. How about 2, 2 and negative 2, 2? Oh, man. There's your parent function. Talk to me about these transformations, and then we'll decide if we have to do them in a particular order. Negative out in front of your function like this. Anyone remember what that's called? I know it's a reflection, but which way? Yeah. So you say reflection over the x-axis. You have to specify where you're reflecting in PreCalc because we have multiple reflections now. All right. For all the points in my heart, who remembers what happens when you throw a 2 inside of your function? Is it this? Or is it this? I mean, it's horizontal. I'm with you there. It is a horizontal. Ah, why is it compression? Yes, because it's weird and backwards. All right, inside the absolute value bars, which are equivalent to parentheses in math, as far as like groupings. So horizontal compression, you could say by 2, or you can say a compression of 1/2. I know what that means. Do you know what that means? What it's going to do is it's going to take your x values and it's going to shrink them by a factor of 2. It's going to divide them by 2. And a reflection over the x-axis, is that going to affect your x's or your y's? That's going to affect your y's. Thank goodness it doesn't matter the order in which we do this. All right. Ready, kids? Let's just start with the reflection. 0, 0. If you reflected it over the x-axis, if you negated your y value, you're still at 0, 0. But then, if you took 0 and you shrunk it by half, you're still at 0, 0. That's weird. Okay. So what if I took the ordered pair 2, 2? If I reflected it over the x-axis, I'd be down here at 2, negative 2. But now I need you to shrink in your x's by a factor of half. So now it's at 1, negative 2. Very good. And then because of symmetry, we're going to end up over here with the next point, huh? Beautiful. Now, I know what you guys are going to tell me, besides that's an ugly graph. You're going to tell me, Bruzo, that's weird, because that really does look like a vertical stretch. I mean, does that look like a vertical stretch to you? Like, if someone just walked in right now and they're like, wait a minute. There are certain functions out there where vertical stretches and horizontal compressions look identical. And the reason this one had this issue is because it was placed at the origin, and it's real hard to see what's going on. When I give you a test, this is what you're going to see. And this is a totally made up problem. You don't see it anywhere, so don't panic. But I'm going to give you like this parent function. And then I'm going to give you, let's see here. Gotta make it up so it makes sense though. This new function. And I'll give you ordered pairs, right? I'll tell you that this number, that this number right here is, I'm just making this up, guys. This is a -6, and this is a 2, and this guy over here is an 8. Why not? So then I would have come back with, okay, this is a -3, and this is a 1, and this is a 4. Does the height of those maxes and mins look like the height has changed anyway? No, it has not. So you can't call this a vertical stretch or anything because the heights are not moving. But what did totally change? Your x-intercepts. What used to be a -6 is now a -3. What used to be a 2 is now a 1. What used to be an 8 is now a 4. What happened? It's a horizontal compression. And now I know you're going to tell me of a half, and I get that, but what does that look like in my function notation? Yes! Do you see how weird this is going to be? So like first you got to figure out what's going on, horizontal compression, give it a name, then you got to figure out what it looks like in the math. This is weird. In the math. Okay. We're going to have a lot of these questions warming up before we test on this, guys. Trust me. This is probably the hardest part of the lesson. Oh boy. All right. This one has 3 transformations. I want you to identify them. I'm going to freeze the screen and the video, and I want you to try to get them in the right order. Now, there are multiple ways to get the right order. There's like 3 different versions of the right order, but there's one very wrong version of the right order. So the wrong order. Don't do that one. See if you can get it. All right, so all 3 of them on the screen are actually correct. So now your job is to figure out what's not correct, so hopefully you didn't write that one down. But what do they all have in common, I guess? Yes, it's the order in which you apply your vertical stretch and your down. What has to come first out of those 2? The vertical stretch has to come first. If your vertical stretch shows up in your list after you shifted down 3, that means you're doing this. So the vertical stretch afterwards would be applied to everybody, and that would change your down 3 to a not down 3. It would be a down 6 then. So no, don't do that. Okay, so the order matters on those 2 vertical components. All right, so now for the fun times, we're going to take our parent function, that poor boring parent function, and we're going to apply those transformations using one of these first 3 orders that we came up with. Whoops, that was supposed to be straight. Which combo do you want to go with? The first one? Okay. So, using this order. All right, Taylor, vertical stretching of 2. Well, 0 stretching doesn't do anything, so it's still there. Now let's shift left 2. Don't forget they're counting by 2s, guys. And then down 3. So that vertex is now right here. All right, this ordered pair, this guy right here, which is currently at 2, 2. Where would I be if I vertically stretched that? So vertically stretching it stretches the y value. So it stays at 2, but then now it's up to 4, 2, 4. And then I have to shift left 2, down 3. So it's right here. So it is at 0, 1. 0, 1, but you got to do them in stages, okay? All right, this ordered pair, which is at -2, 2. If I vertically stretch it by 2, that brings me up to -2, 4. And then we shift left 2 and down 3. And at least I see some symmetry. Oh boy, I ruined it with graphing. Okay, so I know stepping back and trying to look at your graph and go, yeah, sure, that looks right. This is a case where you could check it on the calculator to make sure you graph the proper function. But the idea is, can you do it without a calculator? I don't mind you checking it, but make sure you're doing your homework without a calculator. Like I said, on your homework, they're funky. You're not going to be using a calculator for much of anything. But I think when you guys are executing some homework questions, I think it'd be brilliant of you, A, to use graph paper, B, to use colors, like parent function and new function looking in a different color. Notice how I've been putting some ordered pairs down? I think that's smart, because then you can really think about, okay, I'm vertically stretching, so my y's are getting multiplied by whatever. It's like playing the math hokey pokey, man. This is a lot to think about. Let's do one more question before we're out of time, guys. Look at number 7. I'm not doing the piecewise, so there. We have a cubic function, which goes through the ordered pairs 0, 0, 1, 1, and 2, 8, but also negative 1, negative 1, and negative 2, negative 8. So this is your cubic, oh boy, okay. Yeah, that's your function. I know it's been shifted left 1, but what happens when you put absolute value bars around your entire function on the outside like this? Yes, this is the reflected one, right? Reflected, the negative part. So you're going to take this entire negative part. Let's see if it works this time. You're going to, let's see, Bruzo, you're going to copy and paste. And I'm going to flip, but this time up. Yep. Thanks for that helpful hint, guys. Boom! That's our new guy. All right, so these are gone. Oh, but what did I forget to do? I forgot to remove left 1, so if you would just kindly do this. Which means I have something else wrong, I bet, but whatever. Good news! It didn't matter the order in which I applied that left shift because it had no difference on the reflection. Oh my gosh, that was ugly. Sorry about that, guys. You should see my answer key. It's such gibberish. Okay, your homework assignment is this assignment, guys. Use graph paper. Please use graph paper. This is a beast of an assignment. Do not let it go.